Hello everyone, welcome to my calculus lecture. In this lecture, we study linear approximations and differentials. First, we will talk about linear approximation, and then we are going to move on to differentials. Later, you will see that these two are actually equivalent methods of approximating certain quantities. Okay, so linear approximation. Let us take a look at the following picture first. Okay, so here, the A is supposed to be, some number very close to X. Okay, very close to X. So in this case, the what is that? Delta X, which is going to be same as X minus A, is going to be that very close to zero. Okay, so infinitesimal. In other words, delta x is going to be same as dx. Okay, so in that case, from this picture, it is clear that, right, the slope of line segment joining these 2 points, okay, that's delta y over delta x, okay, so here delta y being f of x minus f of a, so delta y over delta x, so slope of this line segment is going to be actually close to the slope of this tangent line at, tangent line to the curve y equals f of x at the point A. Okay, so this gives us, an idea about, how, an approximation can be done using, this tangent line. So to be more precise, let me write. Right, so here, as I mentioned, a differentiable function f of x can be approximated by the tangent line to y equals f of x at x equals a if x is near a, okay? And so, I explained that, how that's gonna work, what the idea is of that approximation, earlier. Right. So such an approximation, I'm gonna go back there and then talk about the little more details. But such an approximation is called a linear approximation, obviously, because we are using a line, especially tangent line to approximate, the given quantity. Okay, so the linear approximation of a tangent line approximation. Oh, yeah, this is typo. The linear approximation or is supposed to be or tangent line approximation of f at a is given by the following formula. Okay, so I'll fix this typo later on. Okay, so how do you get this, right? So to talk about it, okay, let me go to my notepad. And I probably need to go back to an earlier picture as well. Okay. So with this picture in mind, okay, right. Okay, so if x is near a, okay, so that notation, means that x is near a. So in this case, as we have seen in the picture, delta x, which is same as x minus a is close to zero. In other words, delta x is going to be infinitesimal, okay, infinitesimal. So in other words, infinitesimal case, that delta x becomes, dx, right? Dx. So uh, the slope of a line segment, which is delta y over delta x. Okay, let me go back to the picture here, right? So here, this is delta y, the difference, okay? F of x minus f of a, that's delta y. So delta y over delta x, which is going to be geometrically the slope of a line segment, right? Joining these two points, right? Okay, so that slope is going to be pretty close to the slope of tangent line, which is dy over dx. Okay, right. So delta y over delta x, that's going to be close to, you know, dy by dx. Okay, dy by dx. Okay, which is dy by dx is nothing other than f prime of a, right? Which is the slope of tangent line to y equals f of x at a. Okay, right. So we have this one here. So this implies that delta y, if you solve actually this equation, approximation equation, right? For delta y, that's going to be f prime of a uh, times delta x, right? Times delta x. Okay. On the other hand, this delta y is f of okay, f of x minus f of a, right? F of x minus f of a. So uh, we have the following. So f of x. Yeah, and also on the other hand, this delta x here equals x minus a, right? That's x minus a. So putting these all together, we get f of x minus f of a is approximated by f prime of a times x minus a. And if you solve this for f of x, that equals, oh, not equal, actually, approximated, right? Approximated. So f of x is approximated by f of a plus f prime of a times x minus a. So we got this formula here, right? So this right-hand side, we are going to denote this by L of x, okay? L of x. So what it says is f of x can be approximated by L of x if x is close to the number a, okay? So what is going on here is that f of x, so this f of x is, let me use maybe, different color. So left-hand side, this guy, f of x is the actual quantity. Okay, that's actual quantity. Normally, this actual quantity is difficult to calculate. Okay, so that's difficult to calculate. What I mean by difficult to calculate is by hand. Okay, so by hand. Okay. On the other hand, this L of x, so this guy is approximation. Okay, that's approximation. And this is easier to calculate. By hand. Um, so, for heads up, because if I don't mention this, I think you might be wondering later on, like, when I go over like a certain examples, and then you might say, what's the whole point of doing this? Just the punch a calculator or using computer, you can get the value, nice value, okay, of whatever you want to calculate. And then so why the heck we are doing this, okay? So I don't see a point. So you are going to complain. So have this in mind, by the way, okay? The reason we are studying this is the following. So this kind of a method was used a long time ago when people did not have calculators, when there were no calculators, all the time, okay? So people had to calculate like, for instance, we are going to talk about later, but for instance, like a square root of, let's say, 3.98, okay? It's not the 3.98 is not a perfect square. So, you can't just simply calculate. And then there was no calculator. So, the people had to devise a way to approximate the quantity, okay? Something like a square root of 3.98, all right? So that's the method we are studying. Besides that, the often like students get confused, but they bring like what the value calculated by a calculator, and then say that, oh, this is exact value. No, your computer in many cases cannot calculate like exact value, right? It only calculates actual approximation. So what you may perceive as the exact value, because calculator tells you so. I mean, not the, actually it doesn't tell you, but it returns the value, and you just assume that like it is exact value. But calculators, they don't. In many cases, like other than like what say square root of 4, like square root of a perfect square, it can't calculate like exact value. Okay, it only calculates can calculate approximation. So many cases what you are seeing, as the value, numerical value, right, on your calculator is actually an approximation, not an exact value. And so, how a calculator, calculated those values? Actually, it does use mathematics, of course, something like this. But honestly, this linear approximation is not very accurate. Okay, in terms of accuracy, it's not very accurate approximation. So, of course, your calculator is not using this, linear approximation, but it uses like a more complicated, polynomials, other than, in this case, we are using straight line, tangent line, but, we actually use it more, complicated polynomials like quadratic polynomial, cubic polynomial, and so on and so forth. Okay, so the higher the degree is, the more accurate, the approximation can be. So, in practice, we use like, the quadratic approximation, cubic approximation, so using like the cubic polynomials and so on and so forth. Okay, so not, but the principle is same though. Okay, right. So that's how, calculators also, calculate the values you are seeing. Right. So having said that, uh, so you got the clear idea, right? So let's go back. Right. So here, L of x, right? That's what we found, all right? And this L of x is called linearization, okay? So there is name for it, linearization of f at a, all right? And in fact, you might have noticed, but it is the equation of a tangent line to f at a. So in other words, like I mentioned before, we are approximating, okay, we are approximating, the actual quantity, which is actually for the value of a function at a, at x, right, using this, the tangent line. Okay, so we are going to go over the following three examples. So one at a time. So first example here is find the linearization of f of x, which is given by square root of x plus 3 at a equals 1, and use it to approximate the following two quantities, okay? Square root of 3.98 and square root of 4.01. Okay, so to work on it, let's get to my notepad. Okay, so example. So we have the function here, f of x equals square root of x plus 3, right? Square root of x plus 3, and a equals, so a is given by 1. So, L of x, the linearization, that's going to be, remember the formula, f prime, no, that's f of a plus f prime of a times x minus a. That's the formula, right? That's the formula. Right here, okay? Yeah. All right. So to find it, right? So f of a is going to be square root of a plus 3 plus we have what? F prime of x. That's easy, right? F prime of x is 1 over. Well, in principle, you will have to use, the chain rule. But since x plus 3 is, a linear function, right? So, actually u equals x plus 3, du dx is just 1, right? So, it's just simply 1 over 2 times the square root of x plus 3, right? X plus 3. Okay, so f prime of a is going to be 1 over square root of 2 times the square root of a plus 3 times x minus a. All right, so in this case, since a equals 1, this is going to be square root of, so a equals 1, so square root of 4, that's going to be 2, plus 1 over 2 times 2, that's 4, times x minus 2. Oh, I'm sorry, x minus 1, right? X minus 1. Okay, good. So you know that this can be simplified to the following equation of a line: x over 4 plus 7 over 4. You don't have to write it in this form, okay? You can actually just use this. So it really doesn't matter. But actually, sometimes it does. Sometimes actually leaving, the arrow of x just like this might be easier from calculation point of view, okay? So you might see that later on, okay? So it is not necessarily, advantageous to write it, to simplify and then, write it in this form, okay? All right, I just did it though, but so, uh, so in that case, we are now supposed to calculate square root of 3.98, right? 3.98. So that's x value, okay? So this guy is x. Okay? So that's going to be approximated by L of 3.98, which is going to be 3.98 divided by 4 plus 7 over 4. Now this is some quantity, right, that you can calculate by, oh no, actually there is a, no, actually I made a mistake here, right? No, this is not x, sorry, this is not x. Because this is, right, this is, I, that's f of x, so that's supposed to be square root of x plus 3. That's supposed to be square root of x plus 3. So by comparing, right, so by comparing these two, x plus 3 equals 3.98. So you can easily see that x has to be 0.98, right? X is 0.98. So that's 0.98. That's x value, okay? So this is our x value. And so here also 0.98, and that's something we can actually not easily calculate by hand. And that's going to be, if you calculate, 1.995. Likewise, we are also, going to calculate the following quantity here, right? 4.05, okay? So that is going to be approximated by L of some x. So what would be the x, right? Same thing. So this guy here is this same as square root of x plus 3, right? In other words, x plus 3 has to be 4.05, okay? So x has to be 1.05, isn't it, right? So 1.05. So that equals 1.05 divided by 4 plus 7 over 4, and that's going to be 2.0125. Okay, so it's not bad. Okay. All right. So what's next question? Next question is use a linear approximation to estimate square root of 99.8. You see a difference here, between this question and the earlier question. You see, earlier question case, kindly the value a was given. But in this case, we don't have the value a given. So what do we do? You will have to decide what a is. Okay, what a is. So that's the thing. And also, function was given, but function is not given here either. So you will have to decide what function to use. You will also have to decide what the value of a to use. Okay, so it's becoming a little harder, but actually it's not so. Okay, so to work on it, let's get back to my notepad. Okay, uh, I don't have a space left, so I'm gonna move to a fresh new page. All right, so next example. So we want to calculate square root of it, not calculate, but we want to actually approximate 99.8. Okay, so what's not given, we have to figure out f of x, and also we have to figure out the value a. Now figuring out f of x is not hard at all by looking at the quantity we have. So obviously f of x is going to be square root of x. Okay, square root of x. So really, like the hardest part is like choosing, a right A. So what is right A? Okay, right. So here is the thing, so I have two criteria. So criteria for choosing A. So first criterion is the following. A has to be close to x or x value, right? In this case, x value is going to be, by comparing, you can easily see, x is 99.8. So, A has to be close to x. In this case, x value is 99.8. Okay, 99.8. But being close is not enough. A has to be chosen so that f of a and f prime of a can be calculated by hand. Okay, right? Remember, in this case, we are not, we are not supposed to use a calculator. So meaning that, there's constraint on, the choice of A. So it has to be a number good enough so that, we can easily calculate f of a and f prime of a by hand. So by looking at this function here, and then also what it involves the square root, right? So what would be our best choice for such an a? Well, you have probably an answer, right? A is going to be 100. Okay, so our choice based on these two criteria, right, the best choice is going to be a equals 100. Because a equals 100, so 100 is close to 99.8, and also we can easily calculate, because 100 is a perfect square, 10 squared, right? So we can easily calculate f of x and also f prime of x. Here, f prime of x. F prime of x is 1 over 2 times square root of x, right? Okay, so since we have determined the f of x and also a, so we are ready to go. So we have to calculate the linear approximation f of L of x, right? So L of x equals f prime. Again, let me write down the formula first, not f prime. f of a plus f prime of a times x minus a. Okay, so that's going to be f of 100, which is going to be 10, plus f prime of a is going to be f of 1 over 20, right? 1 over 20, and then times x minus a equals 100, right? 100. So I'm not gonna, in this case, to simplify this, just leave it like that. And so square root of 99.8 is going to be, approximated by L of 99.8, which equals 10 plus 1 over 20 times 99.8 minus 100. Okay, so which is going to be 0.02, right? So that's 0.02. So 0.02 divided by 20, that's going to be, well, actually, that's negative 0.02, right? So it's going to be negative 0.01. So that equals 9.99. Okay, so that will be the approximation to square root of 99.8. Okay. Next example is also same kind, right? So you use linear approximation to estimate cosine 29 degrees. Okay, so here again, we are not given like the function for the linearization, and also the we are not given like a, right? So we have to figure those out to use linear approximation. Okay, right. Okay, so next example here, we want to approximate uh, cosine 29 degrees, right? So obviously from the quantity, by looking at the quantity, it is easy to figure out what f of x should be. That is obviously cosine of x. Okay, so that's the function, right? And what about a? Let's go back to the criteria I wrote, right? For choosing, uh, you know, a right a. So a has to be close to the x value, right? And also a has to be good enough, all right? Has to be chosen so that f of a and f prime of a can be calculated by hand. Okay, so those are the two criteria that you have to have in mind when you try to figure out the value of a. Okay, so in this case, the 1 degree, right, one particular degree that satisfy both criteria would be 30, right, degrees, 30 degrees. Because 30 degrees obviously close to 29 degrees, and also you know, right, I mean the 30 degrees, right, degree measurement, uh, that's one of the special angles where you can easily, I mean, you are supposed to know the values of sine, cosine, tangent, and so on and so forth, right? So that's one of those special angles, right? So that's why also, we can choose it, right? But here is one caution though. The degree measurement is not a number, okay? That's not a number, so you can't use it. When we evaluate approximation, it's gotta be a number, but these guys are not numbers. So we have to convert it to what? There are two measurements, right? Two typical measurements of angles, right? One is degree measurement, and the other one is a radian measurement, right? Degree measurement is not a number, but radian measurement is. Okay, so we are going to convert it to, the radian angle, where we know what this is, right? 30 is pi over 6. Pi over 6. Okay, so now we are ready to calculate the linearization, which is going to be f of a, so, f of pi over 6 plus f prime of pi over 6 times x minus a, which is also pi over 6, right? So that's cosine pi over 6. F prime is a negative sign, right? Negative sign of x. So sine of pi over 6 times x minus pi over 6. Okay, cosine pi over 6, cosine 30, that's you are supposed to know the value, right? That's a very special value that one must know, right? So square root of 3 over 2 minus sine 1 over 2 x minus pi over 6. It's actually helpful to remember, for special case, right? Special angles. Remember the ratio of the three, uh, the size of a right triangle. So in this case, that's 30 over pi over 6. That's 60 pi over 3, right? So in this case, you have what? The following ratio, right? So if so the base is in this case base is going to be square root of 3, and height is 1, and the hypotenuse is going to be 2, right? So we have this ratio. Okay, so if you remember this one, you can easily always, figure out sine, cosine, and also, other like trig values, right? Okay, so we are going to leave it like this, okay? So cosine 29 degrees. Now again, 29 is, so that's going to be x value. However, this is not a number. So we will have to convert it to radian angle, right? That's going to be 29 times 1 degree equals what? Pi over 180. So we have it 29. Okay, so that's going to be 29 pi over 180 radians. Okay, so that's number, so we can use it. All right. So this is going to be approximated by L of 29 pi over 180. All you have to do is to use this formula here, right? We just obtained the linearization. So square root of 3 minus 1 half 29 pi over 180 minus pi over 6, that's same as 30 pi over 180. Okay, so that's going to be negative pi over 180. So we have square root of 3 over 2 plus, the pi over 2 times 180 is 360. Okay, right? So I'm gonna leave it at that. Of course, you can calculate numerical value, for instance, like using pi equals 3.14. So you can calculate it, but I'm gonna just leave it there, right? So that's going to be approximation to cosine 29 degrees. Okay, so it's not bad. Okay, so we are moving on to the next technique to approximate the certain quantities, right? Okay, so this time instead of a linear approximation, we use something called a differential. Actually, some things called differentials, right? So let us take a look at the following example. Picture. Actually, this picture is pretty close to the picture we had earlier. Okay, but there's a little bit of a difference between the certain quantities. So here we are going to consider like delta x, right? Which is increment of x, right, from x to x plus delta x, okay, x plus delta x. So in this case also, just like the previous linear approximation case, delta x is supposed to be a very small quantity, so infinitesimal, okay, which means that delta x is going to be same as dx. So same principle applies, same idea applies. So when delta x is very small, okay, delta x is very small, then the dy by delta y by delta x, okay, so slope of this line segment is going to be close to the slope of the tangent line, which is dy by dx. So that's the idea. So the only quantity, the differences in this case, delta x is gonna be the increment from x to x plus delta x. All right, so that's the difference. So actually you can kind of see that although they come with like different names, linear approximation and differentials, but essentially we are talking about the same method, okay? But different representations, okay? But often depending on the context of a given problem, sometimes using differentials is easier or simpler than linear approximation. But actually, any kind of problem, like so if one problem can be solved by linear approximation, it can be also solved by differentials. okay, and vice versa. All right, so let's moving on. Okay, so we have the following, that so we have it here. Delta y is approximated by dy. That's what we have here, right? So I'm gonna go back to. So in that case, when delta x is very small, it's actually so small, close to zero, that it is close to zero. So it is actually infinitesimal. Then delta x is going to be same as dx, right? When that happens, when delta x is so small that it is the infinitesimal dx, then this delta y is actually actual value delta y, that's delta y, right? Can be close to dy. Okay, delta y can be approximated by dy. So from this picture we can see that, right? So that's hence we have the following: delta y can be approximated by dy, assuming that of course delta x is the close to zero. Okay, close to zero. Right, I didn't write it down, but that's the assumption. Okay, so delta y can be approximated by dy if delta x is small enough so that it is actually same as dx, the infinitesimal. So in that case, we also know that dy by dx is the same as in this picture, right? Dy by dx is the same as the slope of tangent line, which is f prime of x. So dy over dx equals f prime of x. So that's actually also interesting because in the very beginning when I introduced right the derivative, dy by dx was merely the notation, okay, notation, which means the derivative of f with respect to x, so f prime of x, right? So at that time, it was just a notation. But right now, we can see also from this dy and dx, those can be considered as separate quantities. So those are called dx, dy, those are called differentials, okay? So the name differentials. Of course, these are the very, intuitive definition, like very classical, the intuitive definition of differentials. But, in modern mathematics, actually, differentials can be also defined very rigorously. Okay, but we are not going to talk about it. It's way beyond the scope of, our, the calculus class. Okay, so anyway, just have that in mind that in fact, the dy by dx is not merely a notation for f prime of x, but also it is, you can actually consider that as the quantity, dx actually divided by the, so, differential dy divided by another differential dx. Hence, we have the following, right? So delta y is approximated by dy, which equals f prime of x dx. But here, dx equals delta x because delta x is, small enough, very close to zero. So we have so delta y is approximated by f prime of x delta x. So here, delta y is going to be, so when you use differentials, okay, delta y is the actual quantity, which is not easily calculated, okay, which is not easily calculated. That's why we need approximation. On the other hand, the right-hand side, that's approximation, okay, that can be easily calculated. Okay, so we are going to go over, so, the following two examples. So the first one is the following. The radius of a sphere was measured, okay, was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. Okay, So I mean, this kind of thing happens all the time because have that in mind. In reality, no matter how hard you try to measure certain quantity accurately, okay, well, the 100% accuracy is impossible. It doesn't matter how cautious you are. It doesn't matter what kind of equipment that you are using. Okay, still you can't avoid error. That's unavoidable. Okay, right? So having error is inevitable. Right. So that always, so error is something like, we have to live with, right? But often, like from certain like, practical purposes, we, we have to give like a certain, the error bound, right? So, for this purpose, like error has to be at most a certain quantity. Like in this case, at most 0.05 centimeters, right? So with that constraint, so with that error bound, right? The question is, what is going to be? Obviously, when you measure the radius, so it comes with an error, and that error is going to be reflected to, the volume of the sphere, obviously, right? So what is the maximum error in using this value of the radius to compute the volume of the sphere? Okay, so that is the question. Okay, so get to, oh, let's get to my notepad, right? So example here. So we are going to work on this example again using differentials. So all you have to know is the following thing. Delta y is approximated by f prime of x times delta x. Okay, that's a simple formula. Simple formula. Okay, so in our case, delta v. So we are going to compute the volume, right? Volume of a sphere, right? So volume of sphere. So let's call v. This is volume of a sphere. That's the volume of a sphere of radius. Radius r. So as you know, that's going to be 4/3 pi r cubed, right? 4/3 pi r cubed. So that's the volume formula. And the so the here delta v. Okay, delta v is approximated by this formula here. So that's going to be actually, f of x is v. So v prime, okay? So v prime, that's going to be 4 pi r squared, right? Right? 4 pi r squared. And then delta r, delta r. So that's the formula we have, okay? That's the formula we have. That's using differential. Okay. And you know that delta V, actually this is, let me write down. So this guy here, okay, this guy here, that's the actual value, actual error, right? And the volume, V, okay? Right, and that's difficult to calculate. By hand, okay, by hand. But the right hand side here, right, that's approximation. And that's easier to calculate by hand. Good. So here, there is constraint, right? So delta R is less than or equal to, I think if I remember correctly, right, 0.05 centimeters, right? 0.05 centimeters. So maximum allowed, the error in the measurement of R is going to be 0.05, right? Which means that delta V, so delta V, okay, right? So that's approximated by 4 pi. Remember R? So the one, measured, right? That the R radius that was measured was 21 centimeters. So that's going to be 21 squared, right? And so, here in this case, we are going to use a maximum, okay, possible error in the measurement of a radius, right, which is 0.05, so that we can calculate what is that? The maximum error in using that value, the measured value, R equals 21 centimeters, right, to compute the volume of the sphere, right? So, so that's gonna be, yeah, so I should say delta V is approximated by dV, but dV is actually less than or equal to, what is that, 4 pi 21 squared times delta R. I'm going to use this maximum value 0.05, okay, 0.05. So that's going to be, if you use like what, the numerical approximation for pi, like a 3.14, altogether that's going to be 277 cubic centimeters. Okay, so that's going to be maximum, the possible error in the measurement of the V, right? Maximum possible error in the measurement of the volume. Okay, not the measurement, but the maximum error that can be computed is approximately 277 cubic centimeters. Okay, so that's not bad, right? So let's move on to next example. Uh, so we want to approximate square root of 81.1 by two separate methods. So first by linear approximation and also by differentials. Okay. example will illustrate that two actual methods are essentially, same, equivalent. Okay, right. So let me get to my notepad, right, again. So that's going to be our last example, actually last thing, I want to talk about, okay? Right, so example. So we want to calculate square root of 81.1. So the first solution is by linear, okay, linear approximation. Okay, by linear approximation. So we gonna figure out, the f of x in this case, because, we are going to use the linearization L of x, right? So we're gonna figure out f of x, no problem. We used that before, right? Square root of x, obviously. And what is going to be a, right? Again, having those two criteria I mentioned earlier, a has to be close to the x value, which is 81.1. And also, a has to be good enough so that, the square root of a and also 1 over 2 times square root of a, which is f of a, and, the f prime of a can be calculated easily by hand, right? So the number that satisfies those two criteria is obviously 81, right? 81 is a perfect square, 9 squared, right? Okay, so L of x in this case, square root of, right, f of a, which is square root of 81, so that's going to be 9 plus 1 over 2 times the square root of 81, which is 2 times 9, so 1 over 18 times x minus 81. All right, so that's the linearization. And I'm going to leave it like this, okay? So here, square root of 81.1 is going to be, so that, what is that? That's f of x, right? So that's going to be 9 plus 1 over 18. X is, in this case, because we are using the function, okay? We are using the function square root of x. So by comparing, obviously, x is simply 81.1. So 81.1 minus 81. So that's what I'm talking about here, the reason actually I'm leaving it like this is, 81.1 minus 81 is going to be just 0.1. So, that's simpler to calculate. So we have here 0.1 divided by 18, okay? Which is actually 1 over 180. So that's going to be, right, so 9 plus 1 over 180, and that's going to be approximately 9.00555. Actually 5 continuous, but I'm going to just round it, so 5.5556, okay? All right, so that's the approximation we obtained. Now, next, second solution. So this time we are going to use it by differentials, okay? By differentials, right? So, again, we have the formula delta y is approximated by f prime of x, okay, f prime of x, delta x. Okay, so the present form, right? The present form is not actually convenient for us to use to find the approximation. So I'm going to slightly change this, okay? F prime, right? Okay, so remember delta y is from the picture earlier, right? That's going to be f of x plus delta x minus f of x, okay? So, if you solve it for f of x plus delta x, we are going to obtain f of x plus delta x is approximated by f of x plus f prime of x delta x. So, in fact, the right-hand side, if you notice, right, that's precisely the linearization. So, actually, we already see that it is equivalent to linearization. Okay, just with different quantities, slightly different quantities. Okay, so that's the formula we are going to use. So in this case, this guy is going to be the actual quantity. We want to calculate, but difficult to calculate by hand. And right-hand side here is approximation. Okay, approximation, which is easier to calculate. So have that in mind. Right. So all you have to, in this case, what you have to figure out is x as well as delta x. Then you are done. All you have to do is just put them into this formula and then calculate, right? And so how do we figure out x and delta x? Well, no big deal, because f of x plus delta x is the actual quantity. Now, what is the actual quantity? Actual quantity we want to calculate or approximate is square root of 81.1. So which means that x, by comparing x plus delta x, has to be 81.1. So in this case, choosing x, right? For choosing x, we have to use those two criteria, right? X has to be closer to this quantity here, and also it has to be good enough so that f of x and f prime of x can be calculated without a calculator, right? And so, of course, we know what that is. So, obviously, x is going to be 81. And once you choose x, then delta x is automatically determined, right? Delta x is going to be 0.1. So once you have these two quantities determined, then we are set to go. So square root of 81.1 is approximated by f of x, right? F of x is square root of 81, which is 9, plus f prime, 1 over 2 times the square root of 81. That's going to be 18, right? And then multiplied by delta x, 0.1. We had, this is exactly the same value we had earlier, right? Which is 9 plus 1 over 180, which is, right, same, actually approximated by 9.00555, it keeps on going, but I'm going to round it, okay? So 6. Okay, so this is it, folks. All right, so the more details of it, my discussion here in this lecture can be found in my lecture note at the following address. So as usual, again, for your convenience, I made a hyperlink to it. So all you have to do is just click on this, link, and it'll take you to my lecture note, right? And also, if you want to visit my main the blogger site, just click on this word blogger, which is also hyperlinked. Okay, that's the place where you can find my the other lecture notes. Okay, so thank you for watching and listening to my lecture. Okay, bye bye.